So Professor Moustakides he's from Greece, and he got his PhD from Princeton University. Then he was at India for about 4 years. Then he's been at the University of Patras since 1991. As a faculty member first in computer and information sciences, and then technical computer engineering. Then he went back to India for about 4 years, and he's now back at Patras. He's one of the people that started the mathematics and the serious discussion and results of sequential detection with Michel Basville many years ago. And his interest includes sequential analysis, statistical signal processing, and signal processing for communication and hearing aids. And he's telling me he's just about done with a book, that much expected book on which I expect to be the Bible of these problems. So sorry for the too much advertisement, but I've talked to both him and his co-author, and it looks like the book is going to be that. So today he's going to give us a talk on sequential detection over the uniform problem.
Okay, so my talk is going to be, as I said, about sequential detection. We will make an overview, and very quickly I'm going to state some open problems. So I will start with sequential hypothesis testing, and in particular, I'm going to introduce the only known optimum test, which is a sequential probability ratio test. And then I'm going to present an application of the SKRT on a problem on databases. And then I'm going to talk about open problems in sequential hypothesis testing. And then in the second part, we will switch to another problem of sequential analysis, which is, I think, even more important because it finds many applications in practice. And I'm going to present the 3 optimal tests that exist. And then at the end, if we have, then I'm going to talk about open problems. And then at the end, if there is sufficient time, I'm going to discuss decentralized version of the sequential hypothesis and the sequential detection problem. And in fact, here I'm going to talk about sensor network. So what is sequential hypothesis testing? Well, let us recall first what is conventional hypothesis testing. So we have a set of data with a fixed sample size, and this data, they follow 2 possible hypotheses. So the data, they either come from some PDF F sub 0, or they come from some PDF F sub 1. And each time that I have a vector x, I would like to decide whether this x comes from F0 or F1, whether it follows hypothesis 0 or hypothesis 1. And how we do that? Well, we have a function which is a function of the data, and which takes only 2 values, either 0 or 1. Well, if it takes value 0, then it's like saying that the data, they come from H0. When it takes the value 1, it's like saying that the data come from H1. Okay, and how do I pick the optimum decision function? Where there are different formulations. The easiest is the Bayesian, where here I have the error probability that I decide when the data, they follow H0, and this is the type 1 error, as we say, as they say in statistics, or the false alarm in double-E terminology. And then this is the probability of miss, or the type 2 error, when you decide 0 and your data, they really follow H1. And then you have to multiply with the prior probabilities, and you want to minimize this over your decision function. Okay, so this is one possible formulation. The other is the name and person, where you want to minimize the probability of miss subject to a false alarm constraint. You want your false alarm to be no larger than alpha. And we all know that both of these problems, they have a solution, the well-celebrated likelihood ratio test, where you take your data and you compute the likelihood ratio, and whenever the likelihood ratio exceeds some threshold lambda, you decide in favor of H1. When it's smaller than lambda, you decide H0. When it's equal to lambda, you just pick H1 or H0 random. Okay, and now when your data are IID, then this test is equivalent to that. Here we have the product of the individual FIs, and then we take the logarithm, and you can see that here we have the log likelihood ratio, which is the sum of the individual log likelihood ratios. And then you take the log likelihood ratio and you compare it to the threshold. And again, here we see the threshold is H1, if you're below the threshold is H0, and if it's equal, then you write it. Okay, so what is sequential binary hypothesis testing? Now, the data, they are no longer given to me, all of them from the beginning. So at each time instant, I get a new data point. Okay, and then again, I want to test whether all my data will follow H0 or all my data will follow H1. But I don't have all the data from the beginning. Okay, they come one by one as time progresses. So what happens is that at time 1, I have only one data point. And I could, for example, stop here and say, okay, I will use X1 and make a decision. Or I could stop at time 2 and use X1 and X2 and make a decision. Or I can continue this and stop at any time t, or even go further down. Okay, so here I have more possibilities. I can stop at any time I want to, and I can make my decision. And the question is, what is the best way to pick the time that you should stop and make a decision? Okay, so whatever your strategy is, you have to make sure that you decide reliably. That's number 1. And then number 2 is that what we want here is to decide as soon as possible, okay, with the least number of points. And in order to do that, instead of applying just one rule, like the one we had when we had a fixed sample size, here we're going to need 2 rules. So the first rule, what it's going to do is at each time t, it's going to look at the accumulated data and decide whether these data are reliable enough to make a good decision. Okay? And for example, just to illustrate this, at time 1, I get X1. And then I can ask myself, okay, can X1 lead to a reliable decision? So my first rule has to answer this question. Well, most probably in the beginning, this rule is going to say no. So when it says no, then I go to time 2, and I get one more data point. So now I have X1 and X2. And then again, I ask myself, okay, can X1 and X2 lead to a reliable decision? And then the first rule has to answer this question. And again, let's suppose that it says no. And suppose that these no, they repeat themselves until some time, capital T, where I have these data points. And then again, I ask the question. And for the first time, the first rule says yes. Okay, that these data points are sufficient to make a reliable decision. Okay? And at that point, what I'm going to do is I'm going to stop getting more data. And then I will collect my data and make a decision with my familiar decision. So this will be my second. Okay? So a sequential decision rule has 2 parts. One part is the rule that decides when to stop. Okay, and that would be a stopping rule. And then there's the second rule, which is a decision rule that picks between H0 and H1. Now, what is interesting here is that this T is not always the same. It depends on the data that you observe. So in fact, it's the data, in some sense, that decide when you should stop. Okay? So you can run the same rule on one set of data, and T might turn out to be 10, and then the same rules, you can run them in a different set, and this T can be 10,000. Okay? And the question is, why should I use this sequential scheme? It's much more complicated than this simple scheme that we have with a fixed sample size. Okay, well, there is a very serious reason, and it's because, in average, we are going to need much less data samples than in the fixed sample size for the same level of confidence, for the same error probabilities. And when I say much less, as an example, I give you the Gaussian case where we need 5 4 to 5 times less data points in average than the fixed sample size. So this is, I think, a good incentive to use sequential techniques. Okay, so now let me introduce the sequential probability ratio test. And everything, all this sequential analysis started by the SPRT in 45, and it was introduced by Wolf. Okay, so what is the sequential probability ratio test? So we, each time t, we compute the log likelihood ratio. Now, this u of t is a function of time, of course. So at each new time instant, I get a new data point, so u of t changes. Okay? And for example, when my data are IID, then as we saw before, then this is the sum of the individual log likelihoods. And then we can write this simple updating formula where u of t is the previous value of u, and which is updated by the current, by the new log likelihood ratio. Okay? And remember, when we had a fixed sample size, we had only one threshold. Here, we're going to have two thresholds, one positive and one negative. And what is the stopping rule? So we need a rule that's going to tell us when to stop getting more data. Well, that stopping rule is the following. Well, look at u of t, and as long as u of t is inside this interval, AB, then you have to ask for more data. The first time that u of t gets out of this interval, then this is the time to stop. You don't need any more data. And then you can go and make your decision. And what is my decision? What is my decision? When u of t gets out of this interval from above, I will decide 1. When it gets out of this interval from below, then I decide h0. So let me demonstrate this graphically. So this is time, and this is A and B. These are the two thresholds, so they define a strip. And so now I'm going to show how u of t evolves in time, and you can see that, okay, so as long as u of t is inside this strip, then I take more data, and then this is the first time that it exceeds this, it goes out of this strip, and that will be the time when I'm going to stop. Okay? And I'm going to decide h0 because I went out of the strip from below. Okay, so this is the SPRT. And here we're talking about an infinite horizon. There is no limit in the data that I can get. There is an infinite pool of data that I can use. Okay?
And it jumps because of discrete time.
And yes, exactly. And it jumps because it's discrete time. If it's continuous time, I'm going to hit continuous time and continuous path. I'm going to hit exactly the threshold, either the lower or the upper. But here, I have the case where it's discrete time, so you can overshoot the threshold. Okay, so is it optimum? It's not only optimum, it's amazingly optimum. And let's see why. Okay, so remember we said that we have to make sure that our test, that it's going to make a reliable decision. Okay, so reliable decision means that I want to control the errors. Okay, so these are the two errors, and I'm going to control them. I'm going to put a level alpha and a level beta in the first, in type 1 and type 2. So I can control them completely. And then, what else do I want to do? Well, we said that in this case, what we want to do is we want to minimize the number of samples that we're going to need in order to make the decision. Okay, so this is the average number of samples that I need to make my decision when the true hypothesis is h0. And I want this average number to be minimized by selecting properly my stopping rule and my decision rule. But in addition to this, I have another average number of samples. That is when the true data, when the data, they follow h1. Okay, so in fact, I don't have just one optimization problem, I have two. Okay, that's one optimization problem, constraint optimization problem. I have these two constraints, and I want to optimize this subject to these two constraints. And then I have the other optimization problem where I want to minimize this average number subject to these two constraints. I'm sorry. So now, why is it amazing optimality property of SPRT? Because it solves both problems at the same time. Okay? So the same rule, the same detection rule solves two different optimization problems at the same time. Okay? And this is true when you select A and B to satisfy these two inequalities with equality. Okay?
Is this only the IID case or in general?
I will get to that. Okay, so is this true for any type of data? This answers the question. Well, Wold in 48, he proved Wold and Wolfowitz, they proved it for the IID case. Okay, so, and then Filiaev in 67 proved it for the Brownian motion with constant rates. And then Filiaev and Pesquer, they proved it for homogeneous Poisson processes. And these are the only cases where we know that this is true, that we have this double optimality. And it's only for these three cases of processes. I mean, it's basically independent increment process. Okay? So for any other case, we don't know what the optimum is. And this is what's still open. If you put dependence on your data, we don't know what's going on. If you have a problem with multiple hypotheses, if you have hypothesis 1, 2, 3, 4, we don't know what the optimum is. Okay? So, and all these are you know, they've been open for years, and people have tried, you know, many people have tried and failed. And this is, in fact, what makes students not to like sequential analysis. I mean, and statisticians believe that sequential analysis is dead. Okay, so I don't agree with that, but it doesn't matter. So, so let me now present a slightly different version of SPRT, and that would be the case where we have a finite horizon. Okay, so now I don't have an infinite pool of data. I'm allowed to take data only up to time k. Okay, and again, we will consider the case where the data are IID. Well, this problem can also be solved, and the thing is that we no longer have constant threshold over time, but we have the thresholds, they are time dependent. And the thing is that they converge to a single point at k. Okay? So now, if you run your U of t, then, and if it gets out here, then, okay, you will decide h0. As long as it's inside this area, then you're asking for more data. Now, if you exhaust all your data, if you come to time k, then you have a single threshold. Well, there, you're forced to make a decision. And you have only one threshold, so in fact, you're using a line compression. And then this is how you solve. Now, I'm going to present an example where I'm going to use this strategy here. And in fact, we applied all these ideas with Professor Barras 6 years ago in a problem of intruder detection in wireless networks. And that's a very, very interesting problem, but it's kind of expected that all this detection theory will have applications in EE. So this is why I'm going to present an application from databases. Okay, and the problem is called record lineage. Okay, now suppose that you have a database with records. Now each record is identified with a set of attributes. For example, this could be the name, this could be the address, sex, and so on. And so now you want to see if a specific record exists inside this database. And so you identify the record with the corresponding attributes. And you want to see if this record that's identified with these attributes is inside here. So what you're going to do is you're going to take these attributes and compare them to the attributes of each record in the database. And then at some point, you have to decide whether there is a match, or most of the time, when you make the comparisons, you will say that there is a non-match, but you want to see if there is a match, or if you can say that this corresponds to some entry here. Okay, so how are we going to make this comparison? So let me take this record here and put it down, and then what you will do is you will start comparing attribute by attribute. So you compare these pairs, and for simplicity, we are going to assume that the result of this comparison is either a 0 or a 1. 0 means that these two are the same. 0 means that these two are different, and 1 means that these two are the same. Now, you might think that this is a trivial problem because you can say that there is a match when I have everywhere 1s. Well, that's not true, because, for example, here you might have misspelled the name, or here you might have the old address, and here you might have a new address. Okay, so it's a statistical problem. So even if you don't have everywhere 1s, you can still say that there is a match. Okay, so these are my data points. So x1, x2, xk. So I have a finite horizon here. Okay, and we also assume that we know the probability of each xi to take the value 0 or 1 under match, which is hypothesis h1, or non-match, which is hypothesis h0. So it's something very, very simple. You form a likelihood ratio test, and then you decide whether it's a match or a non-match. Well, to make these comparisons, it takes a lot of computing time. So it's very, very interesting if we could do this sequentially. So if we can minimize the number of attribute users, okay? And in fact, I'm going to show you some results that we got by applying this theory, the SPRT theory, on some real database that we got from the US Bureau of the Census. Okay, so here I'm plotting the probability of error versus the average number of attributes. Well, usually in statistics we have the other way around. We plot this as a function of that. But for this problem, it makes more sense to plot the error probability as a function of the number of attributes that we're using. Okay? So now the red line is the test that uses all attributes. Okay? This is the best you can do. You use all your information, that's the best error probability you can get. And that's roughly 3.4 10 to the minus 3. Okay? And now this black line is the error probability of the sequential probability ratio test as a function of the average number of attributes. Now, if my average number is around 1.5, then you can see that I can get I get an error which is roughly an order of magnitude larger than the smallest error. But as I increase the number, the average number, then my the error probability diminishes very, very quickly, and practically at 3.5, 3.6, I get exactly the same error. Okay, it's larger, but the difference is really very, very small. So what I can say is if I can use my sequential test with an average number which is 3.5, 3.6, I get exactly the same error probability, and I'm using 3 times less attributes than the classical test. And in fact, if we look here, at this point, this is a very interesting point, we have an error of 5.5 instead of 3.4. So if I can tolerate this little bit larger error, in fact, I can get by with an average number of 1.8 instead of 10. Okay, so there is a huge gain in attribute usage. And in fact, all this is average. Okay? We're talking about averages. But this problem is very well suited for this idea because you make there are many comparisons that you're making. It's not like you have one set of data, you run it, and that's it. Here, we are going to run the same scheme almost 4,000 times. So it makes sense to talk about averages, okay? And here are the results. Well, we make 3,700 comparisons, and it turns out that if you use the sequential test, then 2,500 of these comparisons are going to use only 3 attributes, and then you can see roughly 454 and so on, and only 68 are going to use 10 attributes. Whereas the classical method, all 3,700, they use 10, okay? And this thing achieves exactly the same error probability like the one that puts all 3,700 puts them here, okay? Yes?
Quick question, in the actual application, how many is K?
Case 10.
That's in the real application?
Yes, yes.
Okay. And second question, what you are listing here are basically the number of attributes that we use in order to unleash whatever what is when you use the test. But for example, the 2502 that you've done with, let's say, 3 attributes, how many were actually correct?
Yeah, but that has to do with their probability, and their
I
probabilities.
understand, but
Yeah.
here what you're giving is, you're telling us that of these 3,703 comparison, you basically decided in 3 steps.
Right.
Right, but how many of these 2502 are actually correct?
There were as many in number as the ones that you were having here. Very small difference. Okay, because the probability, by design, the probabilities of error is the same. But actually, yes, counting them one by one,
You could have variability, right?
yes, you can have variability. I agree. But there was a very small difference between the estimated error probability and the correct probability. Okay. Yeah.
The numbers that you have here, are they from the same data that you used from the previous one?
Yes.
How do I make the connection between these two plots? So before you had the probability of error as a function of the average number of attributes.
Yes.
So the first was, is there a particular reason why you have this piecewise linear function? This is an artifact of the data set that you used?
Well, the piecewise linear comes from the fact that you have discrete, your random variables are discrete. Okay, so this always generates piecewise linear.
But it's also the discrete number of attributes, right? So it gives you a number of 2 or 3, 4. Yeah. Then the average is
Yeah, that's the average. No, but you get this kind of behavior because your data, the random data are discrete. Okay, you take the value 0 and 1. This is fine. Yes?
I'm assuming that you sort the attribute in like reliability. So say, because earlier state you mentioned that the attribute is going to have different probability. Say, if the decision is 1, then you have different probability of the attribute being 1 or 0. So do you sort the attribute by how reliable that attribute is in terms of making a decision? Like say last name is going to be more reliable than say address or phone number.
Okay, that's a very interesting question. But, okay, so what you're asking is how should I order the attributes? Okay, what we did is we have a rule of thumb in our work, but basically what you should do is you should try all different combinations. But there is a rule of thumb which is quite good. I mean, it gave out something that was very close to the optimal. Okay, so in fact, you should try all different combinations. Okay, all different combinations and see which one is the best. Okay, now that's one thing you can do. But there's another thing which is even more interesting. Okay. So you start from one attribute. Depending on what you get, either a 0 or 1, you can decide which attribute you're going to use next. Okay, that's a much more difficult problem. We have solved it, but we didn't dare to publish it because we had an extremely big problem publishing this. I mean, people from databases, they have a difficulty understanding sequential analysis and all that. So. Yes, there is a version of this problem where at each step you can decide what your next attribute should be, depending on what you have already observed. Okay? And that would be the absolute best. But this one is we tried all different combinations and we took the best one. Okay? Yes?
But
Yes.
in practice, if you do that, it's going to be a little worse than using the whole data.
No. This is offline. You do it once. This is something that you will do it once, and it is attached to your database, and that's it. And then, if someone comes and asks for a record, and then you will just use, the rule. Okay, you do it once offline. Okay, you don't do it all the time. Okay, so this is when the error probability is exactly or very, very close to the optimum, and this is when the error probability is 5.5 10 to the minus. So it's a little less than twice the best error probability. And now here you can see that most of the records you make a decision with just one atom, and there's only 18 of the records that they use all attributes, all 10 attributes. Now, as I said, the people in databases, they don't like all these tests and converging boundaries and all that. Now, the nice thing about this problem is that you can find an equivalent test to this statistical test, and you can express it as a binary decision tree. Okay, and people in computer science, they like binary trees. So here, what happens is that you start at this point, so you use your first attribute. If the outcome of this fusion is 0, then you go right. If it's 1, then you go down. Okay? And for example, here, if the usuals of the first attribute is 0, then you go right and you end up at a leaf, so you make your decision. And you say that this is a none. And of course, this corresponds to all these cases. Okay? And if the outcome is 1, then you are at the node, so you're using the second attribute. And if again you get 1, you use the third attribute. And if again you have a 1, then you're at the leaf, and you can decide that there is a match. So what this tree is saying that if you get 3 consecutive 1s, starting from the start, then you can make a decision for match. Okay? But there are also more complicated cases which are taken into account by this tree. And now this work is in collaboration with my good friend and colleague Vasilios Varikis, who is an expert in databases. Okay, so now I'm going to switch to the second problem, which is the change detection problem. And here, again, we're observing sequentially, we're observing a process X of t, and what happens is that at some unknown point in time tau, this process changes its statistics. So this is why I have the beginning in red and then the second part in white. Okay? And what we want to do here is we would like to detect this change. We're not interested in estimating tau. We are only interested in detecting that there is a change. Okay? Now, this problem has an extremely big number of applications in all kinds of fields. And the first application that's been reported is in manufacturing processes. And it's to monitor the quality of the manufacturing process. And that dates back to the 30s. But there are many, many other problems and areas where you can find, you could model the application as a change detection problem. Okay? So let me now introduce the mathematical set of this problem. So we are observing sequentially a process X of t. And this process X of t, from 0 up to tau, this data, they follow some PDF F0. And after tau, they follow some PDF F1. Now, what is tau? There are different models. Tau can be either random, and we can assume that we know some prior distribution, or we can assume that tau is deterministic, but unknown. Now, for F0 and F1, again, there are different cases you can assume, but here we will consider the simplest one, where both of them are known. And again, what we would like to do is, we would like to detect the appearance of tau as soon as possible with the smallest possible detection delay. Okay? So again, we're interested in sequential schemes. So now we have to try to find a good mathematical model for a sequential detection scheme. So whatever you can think of, whatever sequential method you can think of, at each time t, it has to make one of two decisions. Okay? So either decide that before t there was no change in statistics, in which case it will continue taking more data, it will ask for more data, or it will decide that before t there was a change, in which case it's going to stop and issue an alarm. Okay? So whatever your sequential scheme is going to be, it's going to say, take more data, take more data, take more data, and then at some point in time it will say stop. So in fact, your sequential detector is nothing else but a stopping rule. Okay? So, and any stopping rule can also play the role of a sequential detector. So now we have a very solid mathematical modeling for a sequential detector, and that's simply a stopping rule. And then what we will try to do next is we will try to find the best possible stopping rule. Okay, so now in order to do that, we need optimality criteria, and I will start with the first one introduced by Shiryayev in '63. So Shiryayev considered the change time tau to be random with a geometric prime. Okay, and then if t is my stopping rule, then he introduced the following constant factor. Okay, so here we have the detection delay. But we are interested in differences that are positive. This is why we put a plus sign. So this is a positive part. Okay? And why we're interested in positive differences? Because a negative difference is a false alarm, and we take care of false alarms by the probability of false alarms. Okay? And so, so this is the detection delay, and which and each unit of time has a weight of c, and then we add the probability of false alarm. Okay? And so this is the criterion introduced by Shiryayev, and the question is, okay, so how do we define the optimum t? Well, by minimizing this criterion over t. Okay? And so what is the rule that solves this optimization problem? Well, Shiryayev introduced the following probability. So he said, okay, now suppose that I'm at time t, and this is the data that I have observed. Okay? So what is the probability that there was a change before t, given that this information that I have acquired? So this is the posterior probability that there was a change before t. Now, a nice rule of thumb is that if this posterior probability is large enough, then this is evidence that there was a change. And in fact, this is the optimum. And Shiryayev proved that there exists some threshold probability nu, and then whenever pi sub t exceeds nu, this is the time that you will stop, and you will say there was a change. Okay? And is this indeed optimum? Does this rule solve the optimization problem? Yes, but not all the time. We have a solution where the data are IID before and after the change, and we have a solution when the data is around in motion before and after the change with a constant drift, and we have a solution for the Poisson case with a constant rate before and after the change. And in fact, this is very, very easy. Okay? And this is all we have about the optimality of this subgroup. Okay? So now, in '85, Moshe Pollack, he introduced a different criterion, and he assumed that tau is deterministic and unknown. So there is no prior probability. Okay? So he said, okay, so if capital T is my stopping rule, T minus tau is the delay, and I want the average delay conditioned on the event that I stop after the change, okay? Because if I stop before the change, then again, this is a false alarm, okay? Now, for each value of tau, remember tau is deterministic, I can compute this, but I don't know tau, so I'm going to follow a worst case analysis, and so I'm going to put a supreme over tau, okay? And now, how do I define the optimum t? Well, I will minimize this criteria. Yeah, but we didn't say anything about false alarms. Okay, and here is how I control false alarms. Now, t is my stopping time. So this is the average time that I need to stop under the zero measure. Okay, zero means there is no change. So this is the average period between false alarms. And I want this average period to be no less than gamma. Okay, and I control gamma. I can make this average period as big as I want. Okay, so what is the solution to this optimization problem? We have almost the solution for only in discrete time and when the data are IID before and after the change. Okay, and that solution was offered again by Pollack, who suggested to compute this statistic recursive. So every time I'm getting a new data point, I update my statistic as of t like this, okay? And then I compare my statistic to a threshold nu, and the first time that I'm going to exceed my threshold, then this is the time that I will stop, and I will declare that, and I will issue an alarm. And is this optimal? Well, not quite. So this is the performance of this test, and this is the optimum performance, which we don't know. And Pollack was able to show that this difference tends to zero as the false alarm constraint tends to infinity. And in fact, the convergence to zero is quite fast because with very reasonable values of gamma, this is very, very close to zero. Okay, now you might wonder how can we estimate this difference when we don't know the optimum? Well, we don't know the optimum, but we can find a lower bound for its performance and then compare this performance to the lower bound. And in fact, the lower bound of this performance sandwiches the optimum performance. And then we can show that the two boundaries, they converge to each other. And this is how we can make sure that this tends to zero. Okay? And but Pollack was, since the time that he published his result, he was absolutely sure that this test is strictly optimal. And he had every reason to believe that because this test has some very unique characteristics that only optimum schemes, optimum min-max schemes can have. Okay, so he tried for several years to prove strict optimality, and it was one of his students in '97 that came up with a paper that was published in the Annals of Statistics, and he claimed strict optimality of this rule. Okay, so everybody was happy, so we had another optimal scheme besides the one that I'm going to talk about next. And then, unfortunately, in 2006, Gertrude May, who was a graduate student at Caltech, he came up with some comments about the proof, and then it turned out that the proof was in fact wrong, and so that was gone. But Pollack was still convinced that his test was optimal until this year, when Alex Tartakovsky came up with one of his students, he came up with a counterexample. So Alex was able to find a very specific example where he was able to compute exactly what this is, and he was able to propose an alternative test that behaved better, that had a better performance. Okay? And the funny thing is that the same day that Alex got this counterexample, he emailed his counterexample to me, and the same day Professor Pollack, he emailed another proof of optimality of his test, which was obviously wrong. And so now this thing is over, and we know that this test is not optimal. We don't know what the optimum is, but for all practical purposes, this test is extremely good. It's very, very close to the optimum, because this thing is very, very small for reasonable values of gamma. Okay? So now let me go to the last test that I would like to talk about, and which is the most popular test in practice for the change detection problem. Again, the change time tau is deterministic and unknown. And in Lorton in 71, he proposed the following criteria. Okay, so this is more complicated than the previous one, but let's take it one step at a time. So this is the detection delay. We are interested in positive parts. Okay? And I take the expected value of this delay, conditioned on the data before the change. Tau is the time of the change. Okay? And since I don't know this data, well, I'm going to follow worst case analysis. I'm going to consider the data before the change, which are the worst possible. That will maximize this expected value. So here, I have now something that depends only on tau. But I don't know tau. Okay, you don't know tau, you take the supreme over tau. So this is a worst case analysis, but it looks much more difficult than the previous criterion. But it turns out that although this looks more complicated, we can use it to prove optimality of the Q-sum test, which, as I said before, is the most popular test in practice. And by optimality, I mean strict optimality. Okay? So what is the optimum T? It's the one that minimizes this criterion subject to the false alarm constraint. Okay, so let me introduce the Q-sum test. So first of all, what we do is we compute the log likelihood ratio. Now, this depends on the time. So at each time instant, you get a new x of t, so u of t changes. Okay? And then you compute the running minimum of your log likelihood ratio. So you're at time t, you look at all the past values of u, and you select the smallest one. So this is m of t. And then you form this difference, u of t minus the smallest value, but delayed by one time. And then you compare the Q-sum statistic to the threshold. And when the Q-sum statistic exceeds the threshold for the first time, this is when you stop and you return the alarm. This is a very popular test. They use it everywhere, even in cases where we know that it's not optimal. Okay? And for the IID, we have this very simple updating formula where you take your y, the previous way, the positive part, and you add the new log likelihood. Okay, so let's see this graphically. So you have your y is your u of t, how it evolves in time, and then in red you have the running minimum, and at each time t you roughly look at the distance between these two curves. And whenever this distance becomes new or larger than new for the first time, this is where you stop. Okay? So this is the Q-sum test. Now, is it optimal? In discrete time, when Lorton introduced his measure, he was able to prove asymptotic optimality, but not as, but an aspect optimality not as strong as the one that I described in Pollock's case. And then in '86, I proved strict optimality, and then in continuous time, Shiriaev and Weigel proved strict optimality for the Brownian motion case, and then this was extended for Ito processes, which are much more general than Brownian motions. And then now there's under preparation the proof of optimality for the Poisson case. Okay? Open problems. Well, all the rest is open. If you have dependency, we don't know what happens. Here, we always assume that the change is abrupt. Okay, what happens if the change is gradual? It's not abrupt. What happens if your change is a transient change? For example, here, what we say is that when we have a change, this change is persistent. You have an infinite number of data points that we can use to detect the change. Well, what happens if the change after some point it dies out and you return to F0. Now this is very problematic because here you're going to have a non-zero probability not to detect the change, which means that all these expected delays will be infinite. So we have to redefine the problem from the beginning, from scratch, because expected delays, they don't work anymore. Okay, they are all infinite. Okay, so so there are many more open problems. For example, you can be at F0, go to F1 or F2 or F3, so you might jump to different possibilities after the change. Or you might have multiple changes. You can jump from F0 to F1, and then you can jump to F3, and so on. So this is basically what I wanted to say, but
what is known when you don't know F0? Like if you don't want to go and estimate F0, you want to work with
okay, so
for non-parametric version problem.
non-parametric. Well, there are non-parametric versions. Yeah, I think Pollock has done some work.
What's the best result there?
I think Pollock has a very good result for non-parametric. I can give you. I don't remember. But then, for example, if you have like parameters, you can well, again, there are results, but they are asymptotic. I mean, I haven't been very accurate, but because I personally am very much interested in strict optimality, but there's a huge number of results that have to do with asymptotic optimality. Okay, so which I didn't reference, but it's usually a weak asymptotic optimality. Okay, so this way.
And what if the change is introduced strategically and somebody is trying to trick you by introducing this change?
No,
and
suppose
how much
suppose that you are monitoring a system, right, the patient, and then his heart, and then something happens in his heart. So that will change the statistics of your
I
state.
consider this in a security perspective,
Okay.
where the attacker is introducing the change but trying to trick you and doing the change and to make your detection time as long as possible. Do we know anything?
Well, okay, so if he tries to make your detection time as long as possible, most probably his gain is going to be very minimal. So there is always a compromise there. So if he wants, to be hidden, then his gain is going to be very minimal. So if he wants some significant gain, then he will be forced to show himself. And then it depends on you how clever you are to use correctly the data and try to reveal the truth.
Any result?
Yeah, we have
Any result.
one result.
Yeah, we have one result.
Where exactly what you described, that we try to parameterize how strong the attack will be by introducing a parameter that compares the probability of errors of two types. And then we express the good average time, which is the function of this parameter. And it's exactly what we described, that if you want to be a clever attacker and you want to be not easy to detect, you're not going to get so much gain, but then it will take me a lot of time to find. If you want to be too loud, they'll find you quickly. This was in the context of cheating the back-off algorithm in the Mac. And then if you want to steal too much value, they'll catch you very quickly. If you want to be quiet about it, they'll take more time. So this is what we call the strength of the attack.
Yeah. So any other questions?
Yeah, it's like the same thing. If you're going to cheat on your exam,
You made them all, yes. You made them all, yes.
You make it too exact, like two scans rather than the same thing.
Just a comment, but when you have, I remember four.
Well, I'm quite sure that we can extend everything to Levy processes, which include ultimate, depending on Levy is too mathematical. I don't really care. I find I will stop here. I mean, this is really interesting because there are quite a few applications that they use Poisson. You know, I don't know of any application that uses limit rates. So, but I'm quite sure that I can extend because. I prefer to do something else. It's like repeating. This is like repeating ourselves. I mean, it's always the same type. But I mean, Poisson is interesting. It's interesting about here because there are many applications. Going beyond that, I don't think I'm doing.
What about if you have two renewal processes? So you have a renewal process that kicks in, then simply after one of the events takes place, you have another renewal process with a different event distribution that kicks in.
Yeah, at a different time. No, but this is a different problem. You're talking about two consecutive change detection.
No, you won't.
Yeah, one mark of 10 and then switches and then another.
Maybe I make it easy for you because I'm allowing you to change the event time distribution only at event times. Otherwise, I could have in principle, I mean, one way to think about it is that these two renewal processes running in parallel, and at one point you're telling me one takes over the other, and one takes over the other. So in the Poisson case, that doesn't matter because of the memorized property of the exponential. But the renewal case in general is fully matter, especially if you're not in the sense of version.
Just very quick, can you go back to slide number 20? Number.
Which one?
20?
Oh, sorry.
20. 20. 20.
20?
Yeah.
Okay.
Actually, the next one. Yes.
Next.
Next one. Yeah, so this loss function, you add in so the unit of the expected value of t minus tau is time, right? And then you're adding into the probability. So we just choose the c, the constant, the unit is 1 over time.
I need what?
The unit of the constant c that you put in front of the expected value, is that true that that unit of that constant is 1 over time somehow? So that you're not adding.
No, this okay. You're trying to combine two different things here.
Right.
Okay,
But
so
one is a
you're
time.
putting a weight in one. This is the usual Bayesian way to combine things. What you could do is you could say that I will try to minimize this thing, the first part, subject to the full following concern that this probability is smaller than alpha. That's a constraint.
Yeah.
Okay?
It's like Lagrange.
Yeah, this is like Lagrange, exactly.
It's the Lagrange type.
Yeah,
Moustakides.
Yeah, it should be 1 over t because the probability is
It's
unit
non-unit,
less.
it's non-unit.
So you have 1 over t. So I think that the question is, what is the unit of c? It's 1 over time.
There is, let's see,
Some-
yeah,
some
you're right.
sort of
It's 1 over
non-linearity.
t in order to
Some
be,
sort of non-linearity.
yeah, it'll be compatible with, you're right.
Just to make sure to.
Yeah, but if you put seconds here, this will be 1 over a second. But this could be number of samples, so it has no unit. And so this will be a number. Okay?
1 over number of samples. Yes. So the number of samples is going to be integers, and the probability is going to be from 0 to 1. So,
Yeah.
I mean, yeah.
Okay.
Can we hear use this one another if you can?
Oh, okay, I was trying to avoid this, but, okay. This.
Even if someone calls up.
Okay, so now let's see the decentralized version of the two problems. So here we have a sensor network. So we have several sensors that they acquire. Each one acquires its own signal. So sensor 1 has X1, this X2, and so on. Now, when we are in the hypothesis testing problem, what happens is that these data, they follow some F under H0, they follow some F01 PDF. This one is F02, F03, F0K. Under H1, this is F11, this is F12, F13, F1K. And in the hypothesis testing problem, we would like, again, to decide between H0 and H1. So we assume that there is independence across sensors, okay? Now, in the change detection problem, from 0 up to tau, this one follows F01, this one F02, this one F03, F0K. After tau, this is F11, this is F12, F13, F1K. Okay, and we want, again, to detect the appearance of tau. Now, what happens here is that these sensors, they collect data, but they are not allowed to send the raw data directly to the fusion center. That would be the best to do. If the fusion center, which is responsible for any decision, if it could get all possible information, that would be the opposite, okay? But that's the centralized version, okay? But now the sensors, they are allowed to send only very limited information because there is a constraint on the communication rate. And so what we are going to assume is that, for example, each sensor is allowed, well, it's communicating with the fusion center at some times, at a sequence of time instances, which this time instances are random. Okay, so let me discuss how this communication protocol is working and what is sensor 1 what is it sending to the fusion center and what time is. Okay, so remember the SPRT scheme that I had before, so I'm going to repeat it again. And so now, sensor 1 is observing its own likelihood ratio, log likelihood. Okay? And now, this log likelihood ratio, when it exceeds, when it gets out of this strip, then that would be time, for the first time, that would be the time T1. So at this time instant, sensor 1 is going to communicate with the fusion center, and it's going to send the value 0. Okay? And now, before we said that, okay, we stop, but now we are not going to stop, we're going to continue. Okay? Because this is now like a sampling policy. Okay? And normally that I have my log likelihood ratio that's going to continue like this, but what I'm going to do is at this point, I'm going, from my likelihood ratio, I'm going to subtract the value that I had here. Okay? So what I'm going to show is the log likelihood ratio minus this value here. And this is like restarting my log likelihood ratio from 0. Okay? And now you can see that it came out from above, and so that would be the second time instant that sensor 1 is going to communicate to the fusion center, and it's going to send a 1 because the log likelihood ratio, it got out of the strip from above. And this is repeated. So this is like a sampling policy. Now, the fusion center is going to get this 1-bit information. So there is a communication of just 1 bit. Okay? And the fusion center is going to approximate this value with A1, and this value with B1. Okay? Of course, there is an error here. And in fact, if you are allowing me to send more bits, more than 1 bits, then what I'm going to do is I'm going to quantize. I'm going to define some quantization strategy for the overshoot in order to make smaller this error. Okay? But if I'm allowed to send only 1 bit, I will simply send either A1 or B1. Okay? So now, the fusion center needs the log likelihood ratio of everybody. Okay? So what it's going to do is it's going to approximate this global log likelihood ratio. And what happens is that every time it receives a bit from some sensor, let's say sensor I, what it does is it takes the previous approximation that it had, and if the bit is 1, it adds BI, and if it's 0, the new bit, then it adds AI. Okay? And this is how it updates the approximation of the global log likelihood ratio. And then, if you have a hypothesis testing problem, you simply apply a sequential probability ratio test, but not using the exact UT, the exact global UT, because you cannot have it, and you replace it simply with this approximation. Okay? Or you apply a QSUM test when the problem is a change test. And here I'm going to show you the performance of this idea for the hypothesis testing problem. Okay, so this is for 2 sensors, and they are allowed to communicate with the fusion center in average every 4 units of time. Okay, not at every time. So, now, this black line is the performance of the centralized experiment. So the fusion center gets all the information. So this is the best we can do. Okay, and this is all. Now, this blue line is the scheme that I discussed in the previous slides. When we have an infinite number of bits, we can send an infinite number of bits. Okay? Now, you might think that this should be exactly the same with that, but remember, in average, we're allowed to communicate every 4 units of time. So we have less time resolution than this one. Okay? And this is expressed through this distance here. But what is important is that these 2 lines are parallel. So this is a very strong time with asymptotic optimality. But again, this is for an infinite number of bits. Now, if you allow me to send only 1 bit, this is what I get. I get this little dots here. Okay. I cannot guarantee you any error probability. If you want the probability of 10 to the minus 5, you cannot get it with one bit. What you can get is this one. Okay? But you can see that these dots are exactly on top of the optimum, of the infinite bit case. Okay? Now, this red line is the classical scheme that they use, which is what? Every 4 units of time, the sensors, they accumulate their information, they form the likelihood ratio, and they quantize. Okay? And this is a synchronous communication. Our communication is asynchronous. Okay? And this is the continuous line corresponds again to an infinite number of bits. Okay? Now you can see that the blue line is globally better. Why? Because we have a better time resolution. Because these guys, they send at the same time their information. Whereas we are sending it, one sensor can send it now and the other one can send it 1 time instant later. And so in average, we have a better time resolution than sending it synchronous. Okay? And if here we can send only 1 bit, this is what we get. We get this thing here. So you can see a huge difference with respect to our scheme. Okay. And if you allow me to send 2 or 3 bits, then very, very quickly I can populate this line with dots and practically match any error probability that you want. Okay? Even with 3 bits, you can have something which is very, very dense. So that's it.
Very good.
I mean, so I know for the change, detection of change, you consider the state of change happening simultaneously across all sensors. Have you ever considered a case when only part of the network changes and the other part stay the same?
I haven't, but other people have, yes. I think Bernard has, Bernard Valley from Ghana, he has considered that problem.
And is that a result?
Well, he comes up with a scheme, you know, in
They're
terms
bound,
of
so
scheme.
in that case.
But I can give you the reference.
Yeah.
But all these are asymptotics. Okay, so again, this is my let's say my toy research area. I've been working on this here and there, not all the time. It's not like I'm working all the time with this. I like this problem, and whenever I have the time, I work on it. And so this is why I'm interested only in strict amount. Asymptotics I don't care so much. It seems that there is no hope in getting something more with strict amount. So eventually I will turn to asymptotics as well.
Any other questions? Let me ask you a question. Suppose I go to any of the first problem, the easy ones.
Mhm.
Now I do the following. I have several, the application comes from databases or from networks again, but in a different way. The data are not all in one place, or if you don't like that, I have several agents that they can do the test only on part of the attributes.
Mhm.
Then they can exchange information. So I can match that part, you can match that part, you can match that part, and then we exchange information to try to decide quickly. Has it been done? When I have, in other words, a multi-agent scheme where I can look at different parts of the data to do the database is done the matching, or the database itself is distributed, so I can look here, then I compare, then I compare it with normal.
Is this centralized or?
You can do the centralized, but then I would put constraints on what you can send. In other words, in that case, I wouldn't allow you to send all the different centralized because you solve that problem. Or the decentralized version. But the idea is that I will help you cooperate to do the detection, or the estimation, or the change detection.
Yeah, well, I have seen some works where you have a distributed detection, but
This comes to the following instance. Suppose I want to find if there is an attack or intrusion, and I have software with suppose sniffers. Each one of them looks at a particular part of the codes,
okay.
which are the analog of the attributes. But they exchange information, and they do that because each one of them can do each individual detection faster, and you have to correlate the alarms. See if it is strong enough or not. Okay? Or if you have a patient, I'm a patient, you have several instruments of each, and each one of them works, and then I have to decide if it's serious enough or not. This comes in healthcare, with every project in healthcare, and comes out, this is, if you don't do this correlation, it leads to extreme waste in terms of time and resources. Both of them are real problems of this nature, where you don't do everything centralized. Is anything done in that? No, it's set up. The issue is, what's the cheapest or most effective way to collaborate without, of course, putting all the data in the same place? Coordinate.
I think this big guy in Michigan was the name of
Yeah.
or something. Yeah, I think he has done something like that where
On the mathematical side, does anybody formulate that carefully?
he tried to do that and you're allowed to send only one bit of information. It was an extremely difficult paper, and I very much questioned the outcome of
It's
this.
within the network problem in the first part you said. And it also comes when I do searches on the web.
Mhm.
But I can fire several searches and I can match my query on different parts of the data, but I'm allowed to say I agree on that, I don't, but before continuing.
So you are getting partial information from neighbors. No, I haven't seen it.
Any other question? Okay, we can try, if you like, to have more discussion, meet again here or another room at 4 to 5 and discuss more. Otherwise, let's thank